Hello there, and welcome to the Gilethem Project. In our introduction, we talked about building up a speculative history on a fantasy world. But before we can start making societies, we will first need a world for them to inhabit. Or shall we say, worlds? In this episode, we'll be layering the groundworks for a solar system and a main planet. For this project, we'll be taking inspiration from a real-life solar system where it is speculated that life might exist. While not copying every single detail, we'll use the TRAPPIST-1 solar system. The key advantages here are that while the system has many Earth-like rocky worlds, since the star is a red dwarf, all planets orbit within the range that Mercury orbits our Sun, so the system behaves in a completely different way than our own solar system. This gives us room to build a cosmology completely different from that on Earth, while still being grounded in science. The star itself, as a red dwarf, emits light much further into the red spectrum than our Sun, which means that if you were to take a picture, everything would seem redder than on our planet. This, however, won't be a problem, for our brains autocorrect for the shift. Our brain will interpret the same color differently based on its surroundings. It tries to route the color through a perception that must be true because of the rest of what we see. With this in mind, we can still go with the color scheme we are used to in our world, even if the actual colors might be different. Now back to the system. TRAPPIST-1 has 7 rocky planets, about the same size of the Earth. Every star has a so-called Goldilocks zone. This is the region where planets receive the right amount of sunlight to support liquid water on their surfaces. This does not mean that all planets within the Goldilocks zone get liquid water. For example, both Venus and Mars are within the Goldilocks zone of our Sun, yet only Earth supports liquid water. Now, to simulate this on TRAPPIST-1, the 4th, 5th and 6th planet are within the Goldilocks zone. Let's say that only the 4th and the 5th planets have enough atmosphere that can support this, while the 6th lacks greenhouse gases to retain enough heat to have liquid water on its surface. While having 2 habitable planets is already more than we have in our solar system, let's explore the possibility of a third. Tidally locking is a concept that an object that is orbiting around another object has a rotational period similar to the orbital period. This results in it always showing the same side towards the object it is orbiting. This phenomenon actually happened to our moon. When we look up at it, we always see the same side of the moon facing towards Earth, when the so-called far side of the moon is only visible when we go to the other side. Tidally locking is speculated to easily happen to planets around red dwarfs. We will say it happened to our first 3 planets. The first 2 planets are so close to the star that they would likely be too hot to have any form of liquid water. Let's say that our third planet has conditions that will make liquid water possible on its night side and around the terminator zone, a band around the planet in eternal twilight. Recent studies have shown that even tidally locked planets with large oceans can distribute heat over the entire planet quite effectively, even making it possible to have the night side completely ice-free. Now our planet is too close to its star to form a full ocean, but it still holds on to some water. Let's place a large continent on the day side, so that the oceans don't bow away completely, and place smaller continents around the terminator zone. This will allow life to flourish in the twilight, and with ocean currents taken into account, we can have places in eternal night that are still warm enough to support life in our setting. Due to its smaller size and mass compared to Earth, it has a weaker surface gravity, making it possible for life to become way bigger, or it has fewer needs to support its weight. All of these conditions gives us the opportunity to make tropes often found in fantasy, like the eternal twilight of the Feywild, places in eternal darkness and shadow, and places under the burning sun where no regular life would normally survive. Let's call this planet Mokram. Our 5th planet, being the furthest away from the star of all habitable planets, will be receiving the least amount of light. Let's lean into this and make this a world that is largely frozen over, with big glacial ice sheets extending almost towards the equator. Only a narrow band around the equator will have average temperatures above the freezing point of water, also making it a world where there is just life around the narrow band, but one completely different in behavior to Mokram. The enormous ice sheets can lead to an interesting geography. Ice is heavy. If it's on top of a tectonic plate, it can push down the land, making it rise after the point the glaciers subside. This will probably lead to mountain regions forming past the ice sheets, making the geography of the planet quite mountainous. When ice sheets expand and retract, they will also carry rocks and boulders across the land. On Earth we have many examples of rocks that have traveled thousands of kilometers, being taken by the ice sheets of the Pleistocene Ice Age. These rocks can still be found around the world in many places where the ice sheets used to be. Let's say our planet goes through states of more and less extreme glacial periods, leaving many deposits of rock around the planet. The planet itself is way closer to Earth in composition, so let's change another aspect, its rotational period. Due to tidal interactions, it is possible for planets this close to each other to have a fluctuating rotational period. Let's say this happened to our world, fluctuating between a 34 and 46 hour day over the span of a year. While life could probably easily adapt to this new period, the longer nights and colder climate could make for interesting world building. Let's call this planet Kremnur. Mogarem and Kremnur will be studied more closely once we reach them in future episodes. As you might have noticed, we skipped the fourth planet, the planet most Earth-like, which we'll be developing later in this episode. But for now, let's have a greater overlook at our planetary system. Since TRAPPIST-1 is a red dwarf system, the planets all orbit very close to each other. This results that when they are at their closest approach, they will appear clearly visible in the sky. Seen from the surface of our fourth planet, Mogarem and Kremnur will be around 0.55 degrees in the sky during their closest approach, which is slightly larger than the average of our own moon seen from Earth at about 0.52 degrees. This means they are close enough to be able to make out features on the planet and not just appear as wandering stars in the sky. This is of great importance for our world building, for this will reshape early cosmology. For example, the Romans saw the planets wandering the skies, but did not know what they were, so they were considered the gods. Now those same gods still hold their names just as the planet. Even though from Earth we can't see Uranus and Neptune with the naked eye, we still held to the Roman naming convention after their discovery. In our world, the other planets will be known as other places where life exists, where one can observe it with the unaided eye. This will likely lead to a much earlier understanding of orbital mechanics, and due to a topic we'll dive in next episode, interplanetary travel. Now in the TRAPPIST-1 system, all the planets have sunk into an orbital resonance. All orbital times can be described as a part of 24. For example, TRAPPIST-1b orbits 24 times compared to C's 18 times and H's 2 times within the same period. This means that within this 24-part period, that's roughly 36.5 Earth days, all planets will be in the same place in their orbit compared to each other. But in the real system, they all have an offset. Now, while this concept is already interesting, let's shake it up a little bit for world building purposes. A common fantasy trope is an orbital alignment. We can lean into this and make an orbital alignment every period, marked by our 36.5 days. With our system lacking moons, this will give us a nice anchor point to build our months around. The name month does sound a little bit off though, since the word is derived from the word moon. Let's derive our name from alignment and call it an alinth. Each alinth consists of a 36 or 37 day period. This orbital framework will also work for our week. On Earth, the concept of a week has been constructed mainly through cultural heritage, but here there are other observable phenomena. Our main planet has an orbital period of just over 6 days. While on Earth this has become the basis of a year, this time is a bit short for counting years, so probably the weekly calendar will be used for this. Each alinth consists of 6 weeks, each consisting of 6 days. Now remember, our orbital period is slightly longer than a week, but every second alinth is a day longer. This day can be used as a leap day to reset our orbit and calendar every time. Now that our basis for weeks and months are set, let's take a look at what might consist of a year. Perfectly aligning planets this close to each other is inherently unstable. So let's give them a small orbital drift, where due to the planets pushing and pulling on each other, the planets will slowly drift away from one another, and then drift back again until forming a perfect alignment again. We will make this process repeat over a period of 10 alignments, giving us a basis for a year of 365 days. Now that we have a basis for a solar system, let's give it a name. The name where the series is named after, Gilethem. One other oddity we can find at TRAPPIST-1 are frequent reoccurring solar flares. There have been more recent studies identifying 42 of these flares in an 80-hour period. Yet, when I was first conceiving of this world back in 2018, observations with the Kepler Space Telescope had shown a frequency of about 0.38 flares a day. In other words, about 63 hours and 60 minutes apart from each other. Let's lean into this and make it a burst coming out of the star in all directions. Going with the older observations, happening every 63 hours and 60 minutes. Without a strong magnetic field for protection, this extreme solar wind will blow away the atmospheres of our planet, just as what happened on Mars. So let's give all our planets a strong magnetic field so they can hold on to their atmospheres. On Earth, solar wind will be seen as auroras. The more powerful the flare, the further towards the equator these auroras will be seen. Like with the Carrington event in 1859, where auroras could be seen as far south as central Mexico, Hawaii and southern Japan. Our solar flares will be even more powerful, covering each planet in auroras from pole to equator. This occurrence will be the basis of our magic system, as we will be exploring in our next episode. But first, now that we have a good idea of the Gilethem system, let's take a closer look at the 4th planet. On Earth, the form of the continents, the formation of the mountain ranges and archipelagos are all shaped due to plate tectonics. For our 4th planet, we'll be using plate tectonics to discover the world map. There are programs out there that can simulate this for you, but for higher control, I have opted to do it myself. Mountain ranges do not dissolve completely after continental breakup. An example can be seen in the Appalachian Mountains in America and the Scottish Highlands in Europe. Both of these mountain ranges used to be part of a much bigger mountain range back when the continents still formed the supercontinent of Pangaea. Continental drift tore them apart, and now these mountain ranges don't even sit close to a tectonic border anymore. To achieve similar mountain ranges on our world, let's start simulating the planet in a supercontinental state. First, I have drawn the tectonic plates, as seen here. Every continent has an L or an O written on it. The L stands for land plate, like the Eurasian or African plate on Earth, and the O for ocean plate, like the Pacific plate. The brown arrows explain the general movement of these plates, while the red arrows represent the relative movement of the plates at the collision zones. These collision zones are important to determine what type of feature will form at this rift. With these plate tectonics in mind, let's construct a supercontinent, as seen here. This image is still very much abstract, for it is a quick reference for where mountains would be. You might also notice smaller mountain ranges in positions you might not expect mountains if you look at the plate tectonics. These I drew as a remnant of old mountain ranges of an even earlier time and might determine the placement of some hill areas in the future. Now, let's move our tectonic plates around and see where they happened up at our current date, as seen here on this map. Now we can start drawing in the continents again, keeping in mind how the old continents were shaped up and where mountain ranges might still be. Due to these collisions, new mountain ranges have risen up and some archipelagos have formed. For now we finish at this map, but keep in mind we are still world building, and in your construction process nothing is finalized till you say it is. In future maps we will be changing some details when the opportunity to make something more interesting occurs. Let's take a look at our planet's water, but first we'll need to know the height of our land, for water will always flow to its possible lowest location. After this is mapped, we can add in our rivers and lakes, but let's not end with water at that. Ocean currents will influence our land just as much. Warm ocean currents will distribute large amounts of heat near the coast they flow past. For example, the Gulf Stream warms up the air of Europe significantly, while the land of the east coast of North America is way cooler at the same latitude. Besides making the air warmer or cooler, currents also affect precipitation. The cold California current, for example, brings way less rainfall to its coast than the warmer current passing the Amazon rainforest. This means that beside mountains, these currents will determine where we will find forests and deserts. Taking all into account, we come to this map. Now, I just mentioned mountain ranges affecting precipitation. Mountains work really well to block clouds. This results in one side of a mountain range usually getting way more rainfall than the other. A great example here is the Andes mountain range in South America. If we look at the continents, we will clearly see the spawning rainforest of the Amazon, but once we hit the Andes, it stops, while the other side is almost barren. This is something we can observe across the continent, but while we go down, this process suddenly reverses, where the once barren side becomes green and the once green side becomes barren. This is because of the general wind directions. Due to the spinning of the Earth, the Coriolis effect comes into play, mandating the general wind directions on Earth. If we give our planet a similar spin to Earth with a 24-hour rotational period, we can surmise that the same wind directions can be added to our own planet. With all of this in mind, we can come to this map, where red are areas of low rainfall, green are areas of medium rainfall, and blue areas of heavy rainfall. Now add these maps together, clean up some areas to make them more aesthetically pleasing, and we come to this map. Welcome to Trapak. Now that our world is built, we have a place to settle our civilisations, but as it is a fantasy, we will need something more: magic and a basis for religion. We will explore these topics in our next episode. I hope to see you there.